Alright, so the last topic of this course is so-called linear buckling. Buckling is an phenomenon that happens when you apply compressive load onto a structure, and at certain point, when the load exceeds certain value, which we can actually calculate, is where the structure will lose its stability and it will buckle. When we calculate buckling, we use these linear buckling formulas, and the formula is developed by Mr. Euler, and the Euler has developed this formula which describes the maximum buckling force that can be applied to a structure before it will lose its stability. Depending on the structure, depending on the supports on the structure, we get different results, and we will learn now how we can calculate actually those different scenarios. All right. So here we have 5 different scenarios shown in here. These are named Euler 1, 2, 3, and 4 scenarios. The 5th one is a bit of a special case. So what actually is buckling? So you can imagine that if you take for example, your notebook or a ruler and you apply load from the top, you start compressing it. The compressive strength of the material is very high compared to the buckling strength of the structure. So when I start applying load here on the notebook, what actually will happen at some point is that it will buckle like here. Depending on the support of the structure, we get different shapes for buckling, and also we get different strengths against the buckling. So let's take a look at the scenario number 1 in here. So here we have Euler's case number 1, and we have here force at the top pressing this beam, and it's rigidly supported from here. When we increase the force, at some point the beam will buckle, and the shape it will go is like this. So it will bend to the side. Scenario 2 has a support, sliding support at the top, so it cannot move sideways, but it can go up and down. And what will happen at some point when we increase the load is that this beam will buckle like this. Scenario 3 has sliding support with hinge in top, just like scenario 2, but the difference is that at the bottom it's rigidly mounted to ground. And the buckling shape will start linear from there, and then it will do a curve like this. Now you can try to think what would happen in the scenario 4. So in scenario 4, the top end is also fixed against rotation, so it doesn't have hinge at the top or at the bottom, but the top can still move down, so the shape of the buckled beam will be like this. So these are the buckling scenarios, these are the Euler cases, basic cases, and now we can take a look at how do we calculate this force, this maximum force for the given structure against the buckling. So we have here 2 different formulas, and both of these formulas will give you the same results. We will be using only the formula on left. You can try to do the calculations also with the formula on the right, you will get the same results. So in this equation, Pn is the buckling force. Pn equals to buckling force. Units, newtons. Pi, you know what pi is, and then E is the Young's modulus. I, second moment of inertia, and more specifically, it's the second moment of inertia in bending. I will highlight this. It is important that it is specifically the second moment of inertia against bending. And then the L to Ln is the buckling length. And finally, like so. So, all of these other things you already know, you have seen these before, but what is the buckling length and where do we get that? Well, if we take a look underneath each of these Euler scenarios, we see here the Ln, which is now the buckling length. And depending on your structure, depending on the types of support that you have on your structure, you have to look from this list of scenarios which kind of scenario you have, and then you choose the buckling length based on that. So, for example, if we would have a scenario like this number one here, the buckling length that we need to insert into this equation is 2 times the length of the beam. So if the length of the beam was 1000 millimeters, it would mean that the value that we insert in this formula would be 2000. That's how it works. So now you know the basics of buckling calculations. There are 3 exercises that you can try and take a look, and I have provided also the step-by-step calculation for those examples.